Hello and welcome to the mechanics paper of the year 2005 May-June session. And I have provided you with an opportunity to skip to the question of your choice. Just hover your cursor over the scroll bar of the video and you can go to your particular question, because I believe it's not all questions in this paper that are challenging. But feel free to go through all the questions. And let's go to the first question. So in this first question, we are told that there is a small block being pulled along a rough horizontal floor at a constant speed of 1.5 meters per second by a constant force of magnitude 30 newtons acting at an angle of theta degrees upwards from the horizontal. Given that the work done by the force in 20 seconds is 720 joules, we are required to calculate the value of theta. I have underlined some physical quantities here, or features of this situation or question, and one of them is, we are told that this floor is rough. So if this is the surface of the floor and the block is sliding along that floor, when this word is mentioned, rough surface, rough contact, as opposed to smooth surface, smooth contact, when the word rough is mentioned, it should bring into your mind that you're going to consider frictional force, or friction force exists. You may be required to use it. The question could be set in such a way that you don't need it, but the moment it is mentioned, the word rough is mentioned in mechanics paper, be prepared to use frictional force. And of course, if the surface is smooth, we know that friction force is neglected. The other question is the idea of constant speed. In the 2002 paper and even 2003, we encountered this concept of constant speed. The idea of the speed being constant brings in several situations. If the speed of this object is uniform or constant, v, it means that the distance that the object covers over a particular interval of time or time duration, t, can be worked out just using this equation. Distance equals to speed times distance. Distance equals to speed times time. You can work that one out. The other thing that comes into mind is this. If the word constant speed is mentioned and this object is moving in a straight line, it brings in the fact that the velocity of this object is constant. If the velocity of the object is constant, the acceleration of the object is 0, and the resultant force acting on that object is 0. All those are ideas which I'd like you to have in mind. Constant speed means distance can be worked out using that simple equation. Number 2, it means the velocity is constant, and this in situations whereby you're told that it is moving in a straight line. If it moves with a straight line with constant speed, then it means the velocity is uniform. If velocity is uniform, acceleration is 0. If acceleration is 0, resultant force is 0. So I'd like you to note down those ideas, because they are the words that the examiner uses so that the examiner can prompt you to think about particular situations that he or she wants you to use. So don't neglect that. The other one is about constant force. If the force being applied is constant and that force moves over a certain distance, then we can get the work done by the force by just multiplying the force times the distance, if the force is constant that is acting. So let's look at this situation. We've got these this block, it's moving with a uniform speed of 1.5 meters per second, and there is a constant force of magnitude 30 newtons acting at an angle theta upwards from the horizontal. So this time the force is inclined to the horizontal at an angle theta. That is a situation. And the moment I have a situation like this one, I immediately realize that I must resolve this force horizontally and vertically in two directions. So this must be 30, of course, cos theta. That is the horizontal component of that force, 30 cos theta newtons. We are told that given that the work done by this force, look at this word here, work done by the force. When we talk about work done, we usually don't just mention the term work done. It must be complete. Work done by a force, because it is forces which do work. It is forces which do work. Even if it is resistance, even if it is friction, let us mention the word work done by resistance or work done by frictional force. Of course, I have mentioned previously that when it comes to work done by resistance or work done by friction, the examiner normally uses the word work done against resistance or work done against friction or something like that. It means the same thing, because when we say work done by resistance, we will give it a negative sign. But when we talk about work done against resistance, then we just quote the magnitude of the work done and forget about the negative sign, because the negative sign has been taken over by the word against when we use against. It is similar to this. When you calculate acceleration and you find that the acceleration has got a negative sign, you call it deceleration. But when you call it deceleration, you don't write the negative sign. For example, if you work out a question and you find that the acceleration is minus 2 meters per second squared, then you can say the deceleration is equal to 2 meters per second squared. You see, you forget the negative sign. Okay, these are points which are just by the side, but they are very relevant to what we are doing here. Remember, we are looking at this question in detail so that we can see how are the answers arrived at. Are we able to decode what the examiner always expects us to do? You can only do that by one method. You go through as many past papers as possible, and in each one of them, you try to take note of the clues that the examiner keeps on giving. And that is what I'm doing in these revision papers. So I will not tire from reminding you this over and over again. However, let's save some time and go to what they want us to calculate here. They want us to calculate the value of D. Something else comes into mind. The distance moved is horizontal, but the forces applied is at an angle. When we use this equation here, work done is equals to force times distance, the force and the distance must be in the same direction. If they are not, then we go to the trouble of resolving that force in the direction of the distance. In this case, work done by this force, we are going to call it F. Work done by F is going to be equal to the horizontal component of that force, which will be the F itself, cos theta, of course, times the distance moved. And let's see, you can see by analyzing what various aspects of the question mean, even if there was this friction force here, you find that this is one of the questions whereby we've been told that it is rough, there is friction force, but we are not going to use it because everything it can be found from here. What is the work done by the force? It's 720 joules. This is 30 cos theta. The distance, we have already seen how the distance is worked out. It is the constant speed, which is 1.5, times the time, which is 20 seconds. So here I can be able to see that cos theta will be given by, so I'm going to get 720. I divide by, I put everything into brackets here. It is 30 multiplied by 1.5 multiplied by 20. I close the brackets and I get that 0.8. So cos theta is 0.8. And the theta, of course, is going to be equal to the cos inverse of that. So shift cos inverse of the answer that I got there, and I have 36.86. We can say it is 36.9 degrees. There. So we always look for the shortest method to calculate the question or to work out the question, but not a shortcut, but the shortest method to getting the question. Notice that even if a resistance force has been mentioned here, there is some resistance force, we were not able to use it. It's because of analyzing the information given and then looking at what is it that we are required to work out, and we go right ahead and now use that information directly. You will see this one unfold in so many other questions. So let's go to question 2. Now in question 2, we are told that 3 coplanar forces act at a point. You can remember the word coplanar. Coplanar means these are forces in the same plane. The magnitudes of the forces are 5 newtons, 6 newtons, 7 newtons, and the directions in which the forces act are as shown in the diagram. Find the magnitude and direction of the resultant of the 3 forces for 6 marks. You should never miss these 6 marks. In fact, you should get all of them. What is the first step that you need to do here? You look at the diagram, and in your mind, you will have 2 standard directions. Along the incline, perpendicular to the incline, I rule that one out because there is no inclined plane here. The forces horizontal and vertical. You leave those forces which are horizontal, but those ones which are neither vertical nor horizontal, you have to resolve them. So the 5 Newton force must be resolved to the right and vertically upwards, while the 6 Newton force must be resolved to the left, horizontally to the left, and vertically downwards. So I went ahead and drew that diagram just to show you that the 7 Newton force, we don't resolve it because it is already in the standard direction. But the 5 Newton force must be resolved this way and that way. And the component of the 5 Newton force here will be 5 cos 50. And this one will be 5 sine 50. You always resolve twice. This resolved this way and this way with the actual force in between the 2 components. Always make sure that. For example, this one, its components are this one. And this component in this direction, because this angle makes direction with the force itself, just like this direction makes this angle with the force itself, it took the cosine. Similarly, this one will take the cosine. So 6 cos 30, while this one should be 6 sine 30. After using these trigonometrical ratios for quite some time, you should bear in mind that sine 30 is usually 0.5. So 0.5 of 6 is just 3 newtons. So there is no problem with that. However, let's go ahead and get 6 cos of 30. 5.196. We can say it is 5.20. 5.20. The other one is 5 cos 50. And you can see it is 3.21. 3.21 newtons. And the last one is 5 sine 50. And that is 3.83. 3.83 newtons. So you have resolved the necessary forces in order to make sure that all the forces are either acting in the same direction or exactly in opposite direction or perpendicular to each other. There is no other angle. In other words, this force now is no longer there. This one here is no longer there. Neither is this one. No longer there. What I'm having is this 3.83 newtons vertically upwards, 3 newtons vertically downwards, and I can treat these two independently in such a way that because they point in opposite directions, I'm now going to get one force which points in which direction. You can see 3 newtons is less than 3.83 newtons. So I'm going to get one force pointing vertically upwards like this, and it should be the difference between the two, which should be 0.83 newtons. How about these ones? There is this 7 newtons and there is 3.21. I add the two, I get 10.21 newtons. Because when two forces, this one and this one, they are acting in the same direction, to get the resultant of the two, I just need to add them. But when I bring in the one which opposes that, which is 5.2, to combine this and this, I've got to subtract this from this, and the result should be in this direction. And should be 10.21 minus 5.20, and I get 5.01 newtons. These two forces are the two components of the resultant force: the horizontal component and the vertical component. How do I get the resultant? Now I arrange them head to tail. So I just need to slide one of them. Like for example, I slide this one here so that its tail it's in contact with the head of this one. So that becomes the situation. And the resultant is now obtained by drawing a line, a straight line. Sorry for that. My line is a bit crooked. And that will be the resultant. A line, straight line, drawn from the first tail to the last head. And how do I get its magnitude? Pythagoras theorem. Very simple. Should be 5.01 squared plus 0.83 squared, square root of everything over here. And that should give me, so I have 5.01 squared plus 0.83 squared. I get 25.789, and then I find the square root of that answer, and I get 5.078. This is like 5.007. This is approximately 5.10 newtons. Like that. And I've got its magnitude. It's like that. How about the direction? By direction, we just need an angle. I can work out the angle that it makes with the horizontal, this one here, call it theta, and I can say theta is equals to the tan inverse of the opposite, which is 0.83 divided by the 5.01. In other words, tan theta is equals to this ratio. What is theta? And I can work out theta directly just by doing shift tan, then into brackets 0.83. I divide that by 5.10. It is 5.10. 5.10. And I get 9.24. 9.24 degrees. 9.24 degrees. So let me just change that value. So this value is 5.10. 5.10. And that is how you get the magnitude and the direction of the resultant. The magnitude is just a number and a unit. The direction, you've got to, 1, show the angle that you're calculating clearly on the diagram and then work it out. And then you may go ahead and now describe it. For example, you can say the resultant makes an angle of 9.24 degrees in the anti-clockwise direction to the 7 Newton force, because the 7 Newton force was there in the previous diagram. You can see it was there. So we have worked out that and found that the resultant is here. That is the resultant, F, and it makes an angle of 9.24 degrees, like that. Very easy. So what is again the take from this question? Anytime you're given coplanar forces, you should know what it means. And if you're asked to calculate the resultant, the first step is to check, are they in the two standard directions? If they are not, resolve them. Get opposite forces. Subtract the smaller one from the bigger one. Get one force which represents the magnitude of the component of the resultant in that direction. And here, it is important to always think visually. Visually. Let me see whether I had tried to calculate that. No. It's important always to think visually. What do I mean? Draw sketches. Don't just write figures and numbers and everything over there, because you'll have a bit of a problem when you want to see the meaning of whatever physical quantity you are calculating. Diagrams always help us to communicate a lot of information to the examiner. And that is why examiners use diagrams. They also communicate a lot to us. Why don't we use diagrams to communicate to them also? So when we are resolving, let's show them on the diagram. Once we show them on the diagram, then we would be doing the correct thing. So resolve any force which is not in the standard direction. Then subtract for the two forces or three forces or even more forces. If they're in the same direction, add them up. If they're in opposite directions, subtract the smaller one from the bigger one, and the resultant should be in the direction of the bigger one. For example, the 10.21 Newton force and the 5.20 Newton force. You can see they're in opposite directions. So I get the smaller one, subtract it from the bigger one, and the resultant, which is 5.01, should be in the direction of the bigger force, which was 10.21. That is what I mean. So eventually you end up with the two forces which are perpendicular to each other. Those two forces are the components of the resultant force. Arrange them head to tail, use Pythagoras theorem to get the magnitude. Use tan to find the direction of the resultant. And with that, let's go to question number 3. And here we have it. What do we have? We're given that AB are points on the same line of greatest slope of a rough plane inclined at 30 degrees to the horizontal. A is higher up the plane than B, and the distance AB is 2.25 meters. A particle P of mass m kilograms is released from rest at A and reaches B 1.5 seconds later. Find the coefficient of friction between P and the plane. You can see there is a lot of information given here, and there is just one bulk mark, 6 marks. Again, don't allow that 6 marks to scare you or to think that the question is difficult. It is not. Just move through the motions. What are we talking about here? We are talking about an inclined plane. So why don't we put this information on a diagram so that we can see what happens? So I've already drawn the right-angled triangle there. So in the exam, I would also expect you to do the same and then enter the necessary information. You've been told that this inclined plane is inclined to the horizontal at an angle of 30 degrees. Very important. There are 2 points on this inclined AB. A is higher up the plane. So we again put point A here, and that's it. Point A there. And of course there is point B here, and there it is. We are told that the 2 points are separated by a distance of 2.25 meters. That is the distance between them. Call it D, or even call it S, just in case there is a possibility of using equations of uniformly accelerated motion, and you know displacement is represented with S. So just use the symbols which are used in the common equations. All right, we are told that there is a mass, a block. I would maybe draw something like that. It's got mass m. So what do we have? Since it is on an incline, its weight will act vertically downwards, and this one will be mg. That will be its weight. Again, I can go right ahead and say, you know, anything on an inclined plane usually get its 2 components. There is that component which is perpendicular to the incline, and it will be mg cos of this angle. That is where you need that angle. There is the other component which is parallel to the incline, which is mg sine theta. And again, this is the theta that I'm talking about. That's the theta I'm talking about. So understand that if this is the angle that is given on the incline, then the component of the weight down the incline usually takes the sine. The component perpendicular to the incline takes the cosine. And of course, the W, the weight, is always vertically downwards. Of course, this is a rough incline, so there are a few things I might want to include. I might want to include this normal component of the contact force just in case I will require it. And because the object is sliding down the incline, I will include this friction force up the incline like that. Of course, the moment they mention these things, like for example, friction, I will think about, if it's already moving or just about to move, I think about mu r. And in fact, that is what I'm asked to calculate, the coefficient of friction, mu. So what is it that I need? I need the frictional force and I need r. This is one way of getting the mu. What makes me write this one down? You know how you get started in problem solving? You know the first thing that you write down on the question paper? This one is important because I have had students tell me that the moment I received the question paper, I did not know what to write down. I did not know what to write down. This is the trick. To know what to write down, always look at what you have been asked to calculate. Start by thinking about, how do I calculate that? What equations come into mind when I want to calculate that physical quantity? And that is why I've written this. Because friction is mentioned and I can see the object is moving. So definitely this is some form of situation when I use Fr is equals to mu r. There are two situations: limiting equilibrium and when the object is already in motion. That is when I use this equation. And when I look at what I've been asked to calculate, it's mu. So I think about this. That is one of the ways of knowing what to write down. What to write down on the question paper. Another way of knowing what to write down on the question paper is transferring that information that you've been given in the question paper in form of a diagram. Summarize the information. If possible, draw a sketch or write down the physical quantities, rewrite them again on the paper. Rewrite them again. You know what you're doing when you do that? Because you've been doing a lot of practice and you've been writing down this information on paper, the moment you pretend to write down the same information, the senses from your hand, that particular motion sends information to your brain, and your brain immediately starts thinking about the things you've done before that pertains to that particular physical quantity with that symbol. So it is important that when you write down physical quantities, their symbols have got the same symbol all the time. Speed, you use V. Displacement, you use S. Acceleration, you use A. Unless other symbols have been used, always use the same symbol so that whatever you started writing down here can send information to your brain first time, and whatever you had been revising come flooding. And before you know it, you know what to do. Those are the two things you do when you don't know what to write down. Okay, let's proceed and see what we are required to do. So this object will move like this. And because it will move like that, the acceleration it will have will be, there are two forces acting on the object, is this one and this one. So we've been told that it starts from rest. That means U is 0. So the first thing I write on that object, I know that the resultant force F will be equal to ma. What is this resultant force? The force acting in the direction in which the object is moving is mg sine theta, sine 30, minus the frictional force. And I know the friction force is given like this, minus the friction force, which is mu r, is equal to ma. Now, why is it that I need an A here? It might help me because I've got an S, I've got a U, and I'm thinking about an equation such as S is equal to ut plus a half at squared. There's some of the information that are coming into my mind. Yeah. So let's go through the motions. There is this m here, and when I look at the question, the m does not have a value, so it gives me a bit of a problem. But it's not a problem. When you find that a physical quantity has been given in terms of a symbol, don't be discouraged. Just use that symbol throughout. Somewhere, I can guarantee you, it will always cancel out. Let's see. When I see that m and m are there, and I come here, and I know that friction is going to be equal to mu r. And what is r? R is equal to mg cos theta. So I can say this one is going to be equal to mu mg cos theta. A bit crowded there, but I hope you can be able to follow. So this one will be mg sine theta, or sine 30. Let me now bring in the actual value, minus mu mg cos, again I want to use the angle 30 degrees, is equal to MA, and you can see now there is an opportunity for the M to cancel out. What is sine 30? 0.5. What is G? 10. 0.5 of 10 is 5. I'm making this expression to be as simple as possible. Again, what is cos 30? After using the angle 30 so many times during practice, it might occur to you that you know cos of 30, but always confirm with the calculator during the exam. Cos 30 is 0.866 times 10. I get 8.66 mu. It's going to be equal to A. This one is A. Is going to be equal to A. And I know my A in terms of mu. Now, let me come here and see whether this one can help me out. What is, of course, now I have S is equals to U T plus I have A T squared. What is my S? The value of S is 2.25. The value of U is 0, so that makes it 0. Times a half. Now the A is what I've worked out here. 5 minus 8.66 mu into a half A into T squared. T is 1.5 squared. And have I substituted everything? I think I have substituted everything. So let me see. What is 1.5 squared? So here I'm going to have a half into 5 minus 8.66 mu, and I have 1.5 squared is 2.25. Notice how the examiner gives you very comfortable values that cancel out so well. Here I can be able to divide by 2.25 both sides, and I get 1. So multiply both sides by 2. I get on this side I'm going to get 2, and on this other side I'm going to get 5 minus 8.66 mu. And when I rearrange that, I'm going to get my value of mu as 3. My value of mu will be 3 divided by 8.66. And let's see whether that gives me the answer. 3 divided by 8.66. And I get 0.346. And that is how you work out this particular question. You can see that there is a lot of writing here. If someone came in the middle, somewhere where we were working out this question, would think that this is a very difficult question. I've already explained how you get started. In order for you to get started with a question like this one, it's important that you arm yourself with the correct principles, with the correct methods, with the correct concepts. So let us take a short break, and when we come back, we'll continue with the rest of the questions. So what do we have in question 4? In question 4, we are told that particles A and B of mass 0.2 and 0.3 kilograms respectively. So A has got mass 0.2 kilograms and 0.3 kilograms respectively, are connected by a light inextensible string. I have underlined that, and I hope by now when we mention light inextensible strings, it means we are going to assume that they don't stretch, their weights are negligible. Those are the two things that are very important when you mention light inextensible strings. So don't allow that term to confuse you. The string passes over a smooth pulley. Smooth pulley, no friction. At the edge of a rough horizontal table. Rough horizontal table, there is friction. Particle A hangs freely and particle B is in contact with the table. The system is in limiting equilibrium. What does this mean? It means that, 1, we are free to use this equation. Friction force is equal to mu r, where this is the normal component of the contact force, while this is the coefficient of friction, and of course this is the frictional component of the same contact force. So the system is in limiting equilibrium with the string taut and A about to move downwards. A is just about to move downwards. That means B is just about to slide to the left. That means that they're trying to tell me, take the direction of the friction to be to the right. If this is just about to move downwards, then a B is just about to move to the left. That means friction force must be acting to the right, and it is equal to mu r. Now the weight of B, since its mass was 3 kilograms, its weight was 0.3 kilograms, its weight is 3 newtons. The value of R is like that, and as far as this situation is concerned, R is equal to 3 newtons. This string tends to pull it to the right with the tension T, while the same string tends to lift A upwards with the same value of the tension. Again, when it comes to strings, we use two arrows which point towards each other, and the magnitude of the tension is the same. Notice that this and this, they are literally pointing towards each other. The weight of A is 2 newtons. Because the system is in equilibrium, then it means from this situation here, T is equals to 2 newtons. And from this situation here, it means that Fr, friction force, which is equals to mu r, it must be equal to T. That is what it means. And that since T is equals to 2 newtons, then mu r is equals to 2. Next, we are to determine the coefficient of friction between B and the table. And that becomes very easy because now mu will be equal to 2 divided by r. This is 2 divided by 3, which is approximately 0.67. It's just as simple as that. Coefficient of friction, 0.67. Now in part B, the system is now in limiting equilibrium again. It's just about to move, with the string taut and A about to move upwards. Let's see, there's some information we skipped here. A force now acts on the particle B. This force has a vertical component of 1.8 newtons upwards and a horizontal component X directed away from the pulley. Of course, I had created a another slide for part 2. I had created this slide for part 2, so let's use it for this part. There is, of course, its weight is still there. How much was it? 3 newtons. The weight of this one is still 2 newtons. There is still tension here, and this tension is still 2 newtons because it is in equilibrium. So the resultant force on this is 0. Sum of upwards equals sum of downwards. We come here and we see that there is now a force, there is R, don't forget that. But a force has been exerted on B in such a way that the vertical component of this force is 1.8 newtons and its horizontal component is X. That means that that force has been exerted this way to have these two components which are, of course, at 90 degrees with each other. When that force is applied, the system is now in limiting equilibrium with the string taut and about to move upwards. With the string taut and A about to move upwards. This means B is just about to move to the right. That implies the friction force now changes direction and acts in that direction. We are asked to determine the value of X. Again, this one is very easy. All the forces, they are perpendicular to each other or opposite each other, so it's important to know how to get the resultant. For example, over here, when I resolve vertically upwards, I can see the sum of forces upwards, which is R plus 1.8 is equal to 3 newtons. This implies that R is 3 minus 1.8, which is 1.2. This one is so important. You see, we want to guard against this. I mentioned it in the last video. I'm going to mention it again. Here we've got an object whose weight is mg. The R is pointing upwards, is like this. If you've not done very many examples of these questions and encountered different situations of how to calculate R, students normally think that R is always equal to mg. In this case, yes. In the first part of the question, yes. But in the second part, you can see it is not equal to W. Why? There are many forces at play here. So you've got to follow the rules. Move through the motions. The system is in equilibrium. Add forces which are acting in one direction. Together, they should be equal to the sum of the forces act in opposite direction. And I should add here that when you are using this method, always ensure that you show all the forces which are acting on that particle. Isolate it so that you show all the forces. And that is how I get the value of R. Next, forces to the left is T plus friction is equals to X. How much is T? It's 2. How much is friction? We do not know that, but we can work it out. 2. This one is going to be equal to mu R because we know the value of R and we know the value of mu. Let's see. 2 plus mu is 2 over 3. We just worked out that from the last question. And here we've got 1.2. R is 1.2, and this should give us X. So this is 2 plus, this should give us 0.4. This is 0.8 is equals to X, and X is equal to 2.8. 2.8 newtons. As neat and as simple as that. Just go through the motions. Go through each question. Look at what I have written in different colors in this question, because all I did was to copy the question the way it is, but those important clues that the examiner keeps on giving, I'm putting them in different colors so that even when you are reading, you'll be able to identify them and be able to follow when you are reviewing. So I highly recommend that you go through these questions over and over again in order to see what I see. So what is the take from this question? The idea of equilibrium, limiting equilibrium, again, light inextensible strings, rough horizontal surfaces are mentioned, vertical and horizontal components mentioned, and the idea of calculating the normal component of the contact force. The normal component of the contact force. How you calculate that is important. It's not always equal to the weight of the object. It can be greater than the weight of the object. It can be equal to the weight of the object. It can be less than the weight of the object. It can even be equal to 0. As we go through as many questions as possible, you will see how this one unfolds. So let's go to the next question, which is question 5. In question 5, this is definitely about integration and differentiation. Let's see what we have. We are told that a particle P moves along the x-axis in the positive direction. The velocity of the particle P at time t is 0.03 t squared. So at this point, I want to state that velocity as a function of time, because this is how we write it, is given by this expression, 0.03 t squared, meters per second. Now we will remember that for us to get velocity, we usually differentiate the displacement with respect to time. So this point, because in this first part we've been told to find an expression in terms of t for the displacement of P from O after having been given initial conditions. Initial conditions, they always help us to calculate the constant of integration, because once we integrate here, you'll see there will be a constant. We will need to know a method of how to calculate that. Let me look at the initial condition given. We are told that when t is equals to 5, the displacement of P from O is 25. That means x, when t is equals to 5, is 2.5 meters. This is the initial conditions. How does it help us to get the constant of integration? Just watch and see what happens here. At this point, I'm going to write dx to separate these two variables, v dt. And of course, I know the v is this value here. So this one is 0.03 t squared dt. This is what it means by separating the variables. Let me write it clearly. Dx is going to be equal to 0.03 t squared dt. At this point, I can be able to integrate. And when I integrate dx with respect to x, I get x. On the right hand side, I know this one shouldn't be a problem to you, t cubed. And there should be a way of getting rid of that 3 plus the c. And you can see it is this c that we want to get rid of. So this one is going to be equal to 0.01 t cubed plus c. Now this is x as a function of time. So the value of x when t is equal to 5 We've been told it's 2.5. So we go ahead and substitute 5 into this expression. And we're going to get 0.01 times 5 cubed. 5 cubed plus c. So you're going to get 2.5. 5 cubed is 125. 125 divided by 100 is 1.25 plus c. And you can see that c, I subtract 1.25 from both sides, I get 1.25 meters. So our expression here will be x, rather, let me just write it here, will be x will be equal to 0.01 t cubed plus c plus 1.25. 1.25. That is the expression for the displacement, and it is the first part. Second part, find the velocity of p. See, we've got the expression for velocity. If we want to find the velocity at a particular instant of time, we need to find the value of t. So find the velocity of p when its displacement from O is 11.25 meters. It means I have to use the expression for the displacement to get the time when that displacement is 11.25. So for part 2 here, use this empty space here, the displacement is 11.25. This one here is equals to 0.01 t cubed plus 1.25. Subtract 1.25 from both sides, I'm going to get 10. I divide both sides by 0.01. I'm going to get t cubed. T cubed is equals to 1000. That means that the value of t is a cube root of 1000, which is 10 seconds. Remember, I'm supposed to find the velocity when the displacement is this much. So the only way to do that, in order to get the velocity, I need to know the time when the displacement is that much, and I know the time when the displacement is this much. So since I know the time, I come here and say, therefore, velocity when t is equal to 10, I now substitute that value here, 0.03 times 10 squared, which is 100, and I think this one should give me 3 meters per second. And that becomes the answer. It's just as simple as that. When it comes to this type of question where we have to differentiate and integrate, all we need to know is, when do we differentiate? When do we integrate? What does it mean when we get this kind of expression? How do we link what is happening on one side to what is happening on the other side? For example, it would have been very easy for the problem would have been very easy if they had asked me, find the velocity of p when time is 10 seconds. But now they had to give me, find the velocity of p when its displacement is that much, while they know fully well I can't get that velocity without knowing the time. So I've got to analyze that question. I've got to form a pattern. And this is what you get by diligently doing these questions when you're not in a hurry, when you are trying to look at why you do what you do, rather than just getting to to do things in a hurry where sometimes you even don't know why you are doing what you are doing. That is why it is important to do these things slowly, and then you spend a lot of time on it. It helps you to really be able to understand certain key concepts in the subject. And with that, let's go to question 6. And here we have question 6. It's quite wordy. So it's a velocity time graph. Again, what comes into mind when you think about velocity time graphs? Two things. Area is displacement, gradient is acceleration. Let's see how those two concepts unfold. In this question, we are told that the diagram shows the velocity time graph for a lift moving between floors in a building. The graph consists of straight line segments. In the first stage, the lift travels downwards from the ground floor for 5 seconds. So that 5 seconds is when it is moving downwards. And you can see actually the displacement is negative because the displacement is being measured from the ground floor. So when it moves below the ground floor into the basement, then the displacement becomes negative. Coming to rest at the basement after traveling 10 meters, that one is a displacement. And because we have just said that the area represents displacement, this area here, this area will be equal to 10 meters. Find the greatest speed during this stage. So during the first stage, this one is likely to reach a velocity here. So that question did not have that value that I had put there. So I had to remove it because it is this velocity that we are supposed to calculate. So having said that this area, actually you'll find that this V happens to be the height of this triangle. So this one is going to be equal to a half times its base, which is 5, times the height, which is V. And this one will be 20 divided by 5, and V is going to be equal to 4 meters per second. So that is the speed, and it is the answer to part 1. So that is how you work out part 1. Let's look at part 2. The second stage consists of a 10 seconds wait at the basement. From 5 to 15 seconds, 10 seconds. So the lift is not moving. In the third stage, that is this stage here, the lift travels upwards until it comes to rest at a floor 34.5 meters above the basement, arriving 24.5 seconds after the start of the first. That means that this area here is exactly equal to this distance here. That one there. And when you look at it, it is in the shape of the trapezium. So again, in mechanics, there are few shapes. One of them, the triangle, a rectangle or a square, and a trapezium. You should know how to work out the areas of those shapes. We are told the lift accelerates at 2 meters per second squared for the first 3 seconds of the third stage. From 15 seconds to 18 seconds, it is 3 seconds. So the acceleration here is 2 meters per second squared. How do we work out acceleration? We get the gradient. Gradient is equal to this change, which is V minus 0 divided by 18 minus 5, which gives us 3. And remember, this acceleration is 2. So the acceleration is 2, and this is how we work it out. So you can see the gradient of a velocity time graph gives us acceleration. And this is how we get to know that V, therefore, over 3 is equals to 2. V over 3 is equals to 2, implying that V is equals to 6 meters per second. That is the value of this one here, 6 meters per second. So you can see how I'm making use of those two things that I must know about velocity time graphs: the gradient and the area. So far, I've just used the first area, then I used the gradient. Let's look at the part 3. The time during the third stage for which the lift is moving at constant speed. So this time here, we can call it t. This t here. Call it t. Now, we have just said that this shape is a trapezium. The base is from 15 to 24. When we want to get the base, and why am I doing that? So 24.5 minus 15, it will give me 9.5. So from here all the way to here is 9.5. This is A, this is B, and maybe the area that you should remember here, or the formula to remember here when you're working out the area of a trapezium, is equals to a half into A plus B times H. This is always the height. This one here is H. That area we have said is equals to this displacement here is equals to 34.5. This is a half. A is what we are looking for. It's T. B is 9.5. H is what we have just worked out, 6. And now we can be able to work out that question. 6 divided by 2, we get 3. 34.5 divided by 3. I'm dividing both sides by 3. I'll divide by 3. That will give me 11.5. So 11.5 is equals to, I've already opened the brackets here by when I multiplied both sides by 2. I mean, when I divided both sides by 3, I've already opened the bracket. So this is 9.5. And t is going to be equal to 11.5. That answer minus 9.5. And we get 2 seconds. So this answer here is 2 seconds. Very easy. And lastly, we wanted the deceleration of the lift in the final part of the third journey. So I've used area here, I used gradient here, I used area here, and now I want to get the gradient. So in the final part, this is part 4, I want to get the gradient here, this gradient. So I get this value here, which is 0. So I'm actually calculating the gradient, which is acceleration. So it is 0 minus this value here, which is 6. And I have this value here, which is 24.5. Minus, if this is 2, this is 2. So this is 18. And this, we got it to be 2. So this is 20. I subtract 20 here. And I get this is 6 over 4.5. Of course, there is a negative there. So I have 6 divided by 4.5. And there we have it. It is 1.333 recurring. This is like 4 over 3. Negative, of course, meters per second squared. So this is, the acceleration is negative 4 over 3 meters per second squared. So it means that the deceleration, the moment I call it deceleration, remember, I've mentioned this very many times. The examiner will ask you to calculate to get deceleration. But in using these equations, there is nothing like deceleration. It's always acceleration. Deceleration is the name we give to the acceleration if the acceleration carries a negative sign. And that is what we have seen. But when it comes to answering the question, deceleration, we will say that deceleration is equal to 4/3 meters per second squared. And we do not mention the negative sign. So remember that. When the acceleration carries a negative sign, you call it deceleration. When you call it deceleration, when you're quoting its magnitude, don't write the negative sign. And that is exactly what we have done. What is the take from this question? The marks that you earn when you are looking at velocity time graphs, you should be able to earn all of them, because in Mechanics 1, they will always test those two things. Do you know that the gradient represents acceleration? Do you know that the area represents displacement? Therefore, you should be ready to calculate, look for opportunities to calculate the area and look for opportunities to calculate the gradient. That is the trick, and you will get all the marks for a question which involves velocity time graphs. The gradient represents acceleration, while the area represents displacement. And let's go to the last question. Here we are. What do we have? We have a car of mass 1200 kg travels along a horizontal straight road. Horizontal. The road is horizontal. I've mentioned this before. Do you know why we must look at this word horizontal? It's because of energy. If the road is horizontal, the gain in potential energy of that car is 0. Next, the power provided by the car's engine is constant and equal to 20 kilowatts. We're going to see how we use that idea that power is constant. In other words, the power is not changing. The resistance to the car's motion is constant, again, and equal to 500 newtons. There is resistance on that car. The car passes through points A and B with the speeds of 10 meters per second and 25 meters per second. In other words, this is the speed at point A, this is the speed at point B. The car takes a time of this many seconds to move from point A to point B. Find the acceleration of the car at point A. Let's look at what we have here. It is the power which is constant. So, power has been mentioned, resistance has been mentioned, the car is here. There is the car, because it has a certain power, it always exerts a certain driving force FD. It is encountering a certain amount of resistance FR, which is constant, and it is equals to 500 newtons. Let's look at what we know. We know something about power. It's work done divided by time. Work done is equals to force times distance over time. And sometimes we use this equation here. Power is equals to force times speed. There are two situations when we use that equation. Number one is when the speed of the car or the speed of the object is uniform throughout, so we can get the driving force. But when the speed is not uniform, then we will use it at a particular instant of time. For example, see, the speed at point B, A, is 10 meters per second, and the speed at point B is 25 meters per second. That means that the driving force are here and the driving force here, they are different. And at point B, at point A rather, we want to calculate the acceleration of the car at point A. So, let's see. At point A, its speed is 10 meters per second. So when you use the equation, a resultant force is equals to ma. The driving force is Fd minus the resistance force, which is Fr, is equals to ma. But at that instant, I can use the equation power over the speed to get the driving force at that point. This equation should always be able to move like that. The power is 20,000. The speed at that point is 10. The resistance is 500. The mass is 1200. And it is the A which I want. So this will give me 2000 minus 500. It gives me 1500. This is 1200 A. And A is 1500 divided by 1200. What does that give me? By 3, 5, by 3, 4. And this, I think, is 1.25 meters per second per second. That the acceleration the object has at point A. Acceleration at point A is that much. Is the acceleration at point B different from the acceleration at point A? Of course it is. When you look at this equation, the speed at point B, this is constant, this is constant, this is constant, but the speed at point B is different. It's 25. That means the driving force is a little bit smaller, so the acceleration is going to be smaller than this. So that's why they ask us to calculate that. Now you realize that in this question, the acceleration is changing. If the acceleration is changing, the resultant force is also changing. So that means that the driving force is not constant. This one here. Besides, you can even tell that the driving force is not constant by dividing the power, which is constant, by the speed. So let's move over to part 2, which carries a lot of marks, 8 marks, but don't be scared by that. Don't allow the marks which are given at the end of the question to scare you. What you should be worried about is this. Do you understand the clues that the examiner keeps on giving you? Do you understand those clues? And that is the aim of this video. The aim of my videos is not to tell you what the answers are, because I know you can easily get this from elsewhere. The aim of my videos is to explain to you how those answers were arrived at. The aim of my videos is to help you understand the clues that the examiner keeps on giving you in the various mechanics paper. They give these clues over and over again. Those students who understand these clues, they enjoy this paper. So don't allow the questions, the marks to scare you. Let's go move through the motions step by step. Now, you're told by considering work and energy, find the distance AB. In my previous video, the 2004 solution to the 2004 May-June mechanics paper, I told you that there was a question that was using work and energy, and it could also be solved using kinematics. Here, they have limited us to the method to use, because the other methods will not work out. This is why you've got to be very, very careful. Where the examiner dictates to you the method that you have to use, you've got to make sure that you understand everything in the syllabus. And these are some of the things that I've considered in my courses at Udemy. if you go to the description of this video, you'll get a link to my Udemy course. In my Udemy course, I've explained these concepts step by step. So if you've got the time, because you need about just 7 hours to review the whole course, and all the video and all the concepts will be at your palms. So take time, go through that course. Of course, I've given a number of free lectures. Just go through the free lectures that are given there and you will learn something. And maybe by the end of those free lectures, I may have convinced you that there is something that I can be able to teach you a little bit more in that course. And of course there is, because these concepts, I've covered all of them in Mechanics 1. And you just need about 7 hours, 7 continuous hours to review all the concepts there. So let's answer the last part. By considering work and energy, find the distance AB. Now, I've already told you that when a question involves work and energy, there are 4 physical quantities that you need to be sure of. Number 1 is work done by the driving force. And there are 2 ways of getting that work done by the driving force. Work done by the driving force can be given by the driving force times the distance moved, if this driving force is uniform. But we have seen, just by looking at the driving force at point A, the driving force at point A is the power, which is 20,000 divided by 10, which will give us a driving force of 2,000. But the driving force at point B, where the speed is 25, you can see it's different. So the driving force is not constant. The other way you can get the work done is by using the idea of power times time. You see, for you to calculate power, you need to divide the work done by the time. And this is where they told us that the power was constant. You see this one here? The car's engine has a constant. The power provided by the car's engine is constant and equal to 20 kilowatts. So all I need is the time for which this power was exerted, and I can get the work done by that engine. And at this point, because we know that this is what we have to work out, and there is no doubt about it, so I just need to multiply it by the time that is given, 30.5. What I mean by this is this. The easiest way to work out this type of question is to work out each one of the 4 components separately. So the first one is the work done by the driving force. So 20,000 times 30.5, I'm going to get 610,000. 610,000 joules. The next one is the work done by resistance. W FR. And here I get the FR itself. Of course, it must carry a negative sign times the distance. For me to use this equation, then the friction must be constant. Was it constant? Yes. See, the resistance to the motion is constant and equal to 500. So it provides me with an opportunity to use 500 times D, joules. That is the second component. The third component is the gain in potential energy. The gain in potential energy. We check for one thing. Is the height changing? The height is not. The path is horizontal. So this is 0. And the last one is the change in the gain in potential energy, which is a half mv squared minus a half mu squared. So I can have these two in the brackets there, and I have a half The mass is 1200 kg. The speed at point B, which is the final point, is 25. And that 25 is squared. The speed at the initial point is 10 squared. So 25 squared is 625. 10 squared is 100. So 625 minus 100 gives me 525. 525, I multiply it by a half of 1200 is 600. So I multiply it by 600 and I get 315,000. 315,000 joules. And I've got all the four components. How do I put them together? This is how I put them together. I've got to get the work done by external forces is equal to the gain in energy. What are the two external forces? The external forces are the driving force and the resistance. So I've got the work done by the driving force, which is 610,000 plus minus 500D is equal to the gain in potential is 0 plus the gain in kinetic, which is 315,000. So this is the arrangement in order for me to get D. I'm going to get 610,000. I'm going to subtract 315,000. I get 295,000. And the 295,000 I'm going to divide by 500. I divide it by 500 because minus 500 went to the other side of the equal sign, it became positive, and I'm dividing both sides by 500. So this one I divide by 500 and I get 590. So the distance covered here is 590 meters. Let's see what we have here as far as the 8 marks are concerned. Don't worry about those 8 marks. This is what I would advise. When you're dealing with a bulk question like that, even if it has so many details, summarize it like this. Know that you need to use the equation work done by external forces is equals to gain in energy. There are two external forces acting, driving force and resistance. Maybe something to remember here, the work done by resistance is always negative. As far as energies are concerned, you've got potential and kinetic. For potential, check whether the road is horizontal or inclined. If it is inclined, you've got to calculate the gain in potential energy. If the height of the object is increasing, the gain is positive. If the height is decreasing, the gain is negative. Very important. And the moment you work out each one of those 4 bits, work done by driving, work done by resistance, which is always negative, gain in potential, gain in kinetic, you are done. So the 8 marks will be distributed very comfortably to each part of those sections. And that is what we can say about the mechanics paper of May-June 2005. If this is your first time in this channel, I will highly appreciate if you become one of my subscribers. Just subscribe. Just hit that subscription button so that we can share this process of moving through mechanics. The other one is just a challenge. There are some methods that I'm using here, and they will withstand the test of time. One of them is the method that I've used to solve that last part. That method always works. Always works. And I'd like you to show me a question where that method does not work. Otherwise, until next time, when I give you the next paper, which will be May, June 2006, continue solving the question. Continue looking at these videos. Take time. Go through the questions over and over again. I've even made it simpler for you. In the timestamps there, you are able to go to the question of your choice. And I'll see you next time. Bye-bye.